Torch quantized batch norm. Description: a quantized version of the batch normalization operation that applies a learned affine transformation to the output. It is a layer that normalizes the input over a mini batch. It is a common layer used in convolutional neural networks. It helps to improve the performance of the network by reducing the variance of the activations and making the training process more stable. Inputs. Input: a quantized tensor of the input data. Weight: a quantized tensor representing the learnable scaling factor for each channel. Bias: a quantized tensor representing the learnable bias for each channel. Mean: a quantized tensor representing the running mean of the input data. Inverse estimate: a quantized tensor representing the running inverse standard deviation of the input data. Apes: a scalar value that is added to the variance to avoid division by zero. This value is used for numerical stability. Outputs. Output: a quantized tensor containing the normalized input data. Steps. The input data is first normalized by subtracting the running mean and dividing by the running standard deviation. The normalized data is then multiplied by the learnable scaling factor weight and added to the learnable bias. Challenges and fixes. Challenge 1: quantization can lead to a loss of precision, which can result in a decrease in the accuracy of the model. Sample use case that resulted in Challenge 1: the use of quantized batch normalization in a model trained on a dataset with a large number of classes. Fixes to Challenge 1. Use a higher precision quantization scheme. Use a different quantization scheme, such as post-training quantization or quantization-aware training. Use a different normalization layer, such as layer normalization or instance normalization. Challenge 2: quantized batch normalization can be computationally expensive, especially when the input data is large. Sample use case that resulted in Challenge 2: the use of quantized batch normalization in a model with a large number of layers or a large input size. Fixes to Challenge 2. Use a more efficient quantization scheme. Use a different normalization layer, such as layer normalization or instance normalization. Use a different hardware platform, such as a GPU or a specialized hardware accelerator. Challenge 3: quantized batch normalization can be difficult to debug, as it is a complex operation. Sample use case that resulted in Challenge 3: the use of quantized batch normalization in a model with a large number of layers or a large input size. Fixes to Challenge 3. Use a debugger that supports quantized operations. Use a logging framework to track the values of the inputs and outputs of the quantized batch normalization layer. Use a visualization tool to inspect the activations of the quantized batch normalization layer. Torch. Quantized maxpool 1D. Description: this function performs a max pooling operation on a quantized tensor along a specified dimension. Inputs. Input: a quantized tensor of shape n, c, l, where n is the batch size, c is the number of channels, and l is the length of the sequence. Kernel size: the size of the window to apply the max operation. Stride: the stride of the window. Defaults to kernel size. Padding: implicit paddings on both sides of the input. Defaults to 0. Dilation: the spacing between kernel elements. Defaults to 1. Output: a quantized tensor containing the result of the max pooling operation. Steps. The input tensor is divided into overlapping windows of size kernel size. The maximum value within each window is selected. The selected values are arranged into an output tensor. Challenge 1: the input tensor must be a quantized tensor. Sample use case that resulted in Challenge 1: trying to pass a float tensor to the function. Fixes to challenge 1. Convert the input tensor to a quantized tensor using pay. Torch. Quantize a tensor function. Challenge 2. The kernel size, stride, padding, and dilation parameters must be integers. Sample use case that resulted in challenge 2. Passing a float or a list of floats as the kernel size parameter. Fixes to challenge 2. Ensure that all parameters are integers. Challenge 3. The kernel size, stride, padding, and dilation parameters must be positive integers. Sample use case that resulted in challenge 3. Passing a negative integer as the kernel size parameter. Fixes to challenge 3. Ensure that all parameters are positive integers. Challenge 4. The kernel size, stride, padding, and dilation parameters must be less than or equal to the length of the input tensor. Sample use case that resulted in challenge 4. Passing a kernel size that is larger than the length of the input tensor. Fixes to challenge 4. Ensure that all parameters are less than or equal to the length of the input tensor. Torch. NN. Quantized, functional, maxpool 2D. Description. The torch, NN, quantized, functional, maxpool 2D function performs a 2D max pooling operation on quantized input tensors. It slides a window over the input, taking the maximum value within each window. Inputs. Input the quantized input tensor. It should have shape N, C, H, W, where N is the batch size, C is the number of channels, H is the height, and W is the width. Kernel size. The size of the window can be an integer or a tuple list of 2 integers. Kernel height. Kernel width. Stride. The stride of the window can be an integer or a tuple list of 2 integers. Stride height. Stride width. Defaults to kernel size. Padding. The amount of padding applied to the input tensor can be an integer or a tuple list of 2 integers per 8. Pad width. Defaults to 0. Dilation. The spacing between elements within the window can be an integer or a tuple list of 2 integers. Dilation height. Dilation width. Defaults to 1. Seal mode. If true, the output size is calculated with seal instead of flow. This can lead to an output size that is slightly larger than expected. Defaults to false. Outputs. Output. The output tensor after max pooling. It has shape N, C, height, width, where height and width are the output height and width, respectively. Steps. For each window in the input tensor, the maximum value is computed. The maximum values are then assembled into the output tensor. Challenges and fixes. Challenge 1. Seal mode can produce an output tensor with a different size than expected if the input tensor has a non-standard size. Sample use case. Input tensor with height and width divisible by 3. Kernel size and stride are both 3. Seal mode is set to true. Fixes. The output tensor will have a height and width that are slightly larger than expected. This is due to the seal operation used in calculating the output size. To avoid this, it is recommended to use a padding value that ensures the output size is divisible by the kernel size. Challenge 2. Padding can cause the output tensor to have a different size than expected if it is not applied correctly. Sample use case. Input tensor has a size that is not divisible by the kernel size. Padding is applied incorrectly. Fixes. It is important to apply padding correctly to ensure the output tensor has the desired size. For example, if the input tensor has a size that is not divisible by the kernel size, then padding can be used to make the size divisible.